So we're going to talk about the new type of the measurement of the angle rotation, which is the radian. And the radian, as we keep moving on, we'll be able to know why we generally use the radian in terms of trigonometric functions. So firstly, let's start by thinking or defining what is the definition for the angle or the angle rotations. The angle is an amount that is formed between the terminal line and its starting initial segments. So these are two segments that will form an angle measurement or rotation. So let's say from this point all the way down here, we will call it as a starting line, or we also call it as an initial line where the angle's rotation will start. And the ending line here, where we'll notate it as a terminal line, is a line where the angle is actually formed. And let's say that the angle that is formed between this terminal line and a starting line as theta. And theta is just a notation that includes the degrees, also the radians that we're going to talk about in these videos. But we don't know what type of the angle measurement it is notated, so let's just notate this as an angle. And this is the definition of the angle, which is an amount that is formed between the terminal line and a starting line. And we usually have the two ways to notate this angle. The first way to notate this angle, again, like I just said, is degrees. And for degrees, we don't have to explain what that is because we usually use it in our daily life. So for example, there are 30 degrees, 45 degrees, 90 degrees, 60 degrees, and the 90 degrees, for example. And the second way to think about the angle rotation is the radian, where we're going to talk about it in this video. And the radian, if we talk about it briefly, without saying where did it come from, the radian is basically an expression where we notate the angle measurements in terms of the real number. And we might say what is the real number, and we already learned in previous videos where the real number states for just numbers. So for example, the real number can be either 1, 4, 5.7, decimal, or a fraction 1 over 2, or the numbers like pi or e. And we might get confused, why is the pi a number or a real number, because it looks like just a word. But pi, we need to know that the pi is a short letter for 3.14 something on, and we call this whole number as a pi. So pi is a word, not a word or a letter. This pi is an expression of a real number. So, like this kind of real number, but we can't write the negative because there is no such thing like a negative distance or amount. So in a positive distance, we are talking about a real number. And in terms of radians, we generally use the positive number, and this is what the radian is. And for the radian, it was generated, or it came from this sector, and we already know what this sector is. The sector's definition is the part of a circle formed with radius and the arc length, which is circumference for our circle. So the sector, which is part of a circle, where I wrote the definition here, from this sector we will be able to define the radian. And the radian is kind of a ratio before we start what is the sector. So let's say there is a sector that looks like this. It looks like this, for example. And again, this is a sector. And if you're thinking about the sector, then from this point, which is going to be the center for the sector, and all the way down to the end of the vertex here, we will call the straight line as the radius. Just like the radius, which is half of the diameter in our circle. And if this is radius, then also the point from all the way down here, every straight line in our sector is going to be the radius for our circle. and we see kind of a curved line here, and the curved line is part of a circumference for our circle, but it's not a total circumference, so we call it as the arc length for a sector. And with these two things, with the radius of our circle, and it was generated into a sector, and the arc length, which is a curved line per the circumference, then the sector will be formed. And inside the sector, we define the radian. So we define the radian. Let's say the radius, length of the radius is 1. That means this length of the radius is also 1, where this length and this length are exactly equivalent as 1. Then if you also set the arc length as 1, which means when the radius of our circle, which is the half of the diameter, so the radius in our sector and the radius in our sector, as well as the arc length of our sector is equal to 1, when the arc length is exactly equivalent with the radius of our circle, then we define an angle between these two types of lengths, radius and arc lengths, as a theta. But this theta, in terms of a radian, which is an angle in terms of real numbers, like a number 145.7, 1 over 2 pi e, and on and on, like this type, we define the radian as 1. So again, this will happen when the radius of our sector is 1, and also the arc length of our sector is 1. Then the radian, which is being formed, which is a angle that is being formed between those two lengths, we define it as a positive 1. So from here, we might think about the new definition of a radian. In terms of a sector without thinking of its formula. So basically, the definition of the radian will be a measurement of the angle that expresses the ratios between radius and the arc lengths in sector. So the radian in terms of the sector, we can define it as a measurement of the angle that expresses the ratios, and the ratios is the most important thing in our sector. The radian expresses the ratios between the radius of our circle, not our circle but sector, which is half of diameter, as well as the arc lengths in our sector. And this is what the definition for the radian is. So again, if we go back to our original questions, when the radius is 1, and when the arc length is 1, which means the ratio between the radius of our sector and the ratio of the arc length is 1, then the radian, which is the angle that is formed in terms of all real number, is going to be 1. And the thing that we need to be interested in is our ratios. The ratios between the radius of our sector as well as part of the circumference of a circle, which we call it as an arc length. And this is the basic definition for the radian in our sector. Let's think about two more examples to know exactly about the radians and derive its formula. So the second example is a sector with the radius, which is the half of diameter, as 1, and the arc length as 2, like this sector. So this is a sector with the radius of 1 and the arc length is 2. And we always need to remember that the radius of the sector is we are always assuming that the radius of the sector is 1 unless something else is stated. And in this case, the arc length increased from 1, and it doesn't always have to be 1 for all arc lengths because this is the ratios. So the arc length grew 2 times larger, and we want to define the angle that is between this arc length and 2 radius. And if this radius is 1, then this one is also going to be equal to the radius of 1. And if you want to solve for this data, and the data again is the angle measurements, which is notated in terms of the radian, should be something. And if the radius is 1 and the arc length is 2, we define the radian as 2. And again, if the radius for our circle is 1 and the arc length for our sector is 2, then we define the angle theta between two radius and the arc lengths, which is noted as the radian, as 2. And this is the reason why we could do is because the radian is the ratios between our radius and the arc lengths. And from here we can also remember that the ratios of arc lengths and the radian is equal to this theta. So this was the second example for our sector. And let's think about the last one, which is a sector with the radius, which is half of the diameter of 1, and the arc length, which is a curved line that is part of the circumference of the circle, as 1/2 in our sector. And now we can remember that the radius for the sector is always 1 now, unless something else is stated. So that means the angle, only thing that are different is this angle rotations that makes the arc length bigger. In this case it's bigger, but in the second case it will be smaller, since we know that the arc length in this case is 1/2, which went 2 times smaller than the first one. So let's draw a sector that satisfies the radius of 1 and the arc length of 1/2. So this is a sector that satisfies the radius of 1 and the arc length of 1/2. So the radius is 1 and the arc length is 1/2. Now we can see that the arc length shrinked from 1 to 1/2. And again, the radian shows the ratios between the radius of our sector and the arc length of our sector. And if they ask us to solve for this theta, which is an angle measurement in terms of the radian, then it is defined when the radius of our sector is 1 and the arc length is 1/2, then the radian is defined as 1/2. And again, if the radius of a circle is 1, because the radian is the ratios and the arc length is 1/2, then the data, which is noted in terms of radian, is defined to be 1/2. And this will happen when the radius is 1 and the arc length is 1/2. And we can see some relationship between the radius of our sector, the arc length of our sector, and the angle that is data that is formed with the radian. So using these three informations, we can derive a formula between the arc length, radian, and the radius. So before I do this, let's move this down for more spaces. So again, the radian is the ratios between the radius of our sector and the arc length. And for the formula, if you let the arc length of our sector as the length L, and if you let the radius for our sector as R, and if we let the angle measurement beside the arc length and the radius, which is formed in terms of the radian, as theta, we can drive a formula that looks like this. And this formula shows the proportions or ratios between arc length and the radius. So the formula will be L is equal to R times theta. And this means the L value, which is the arc length, is same thing with the radius for our sector times the angle measurements in terms of radian. And this shows the ratios between the L, which is the arc length, R, which is the radius, and we express those terms in terms of the angle radian. Now if we go back to our equations, we can actually input our formula. We got L is equal to R theta, what was the L in this case? The L, which is an arc length, was 1. And that should be equal to R, which is the radius for our sector, which was equal to 1, times the data, and we define data, which is a angle measurement between 3 values, as positive 1. And 1 thus equal to 1 times 1. Now let's get to the second one, where L, arc length, is equal to the radius of our sector times the data. The L value, which was the arc length, was 2. And that is equal to the radius, which is R for our sector, which is 1, times the data. And we define the data angle measurement, which is in terms of radian, as 2 at that case. And 2 times 1 thus equal to 2. And lastly, for the sector where the arc length shrinked instead of increased, we can apply L is equal to R data, and the L value, which is an arc length, is 1/2. And in 1/2 is same thing with the radius, which is 1, times the data measurement, which is an angle rotations in terms of radian, is equal to 1/2. And 1/2 times 1 thus equal to 1/2. So we could prove that L, which is an arc length, is equal to R data, which is the radius times the angle measurement, is a true statement when it comes to solving our sector radians. So this was the basic introduction for the radians. And if you review what we did, there were angles measurements. The angle was the form or the amount that is being formed between the terminal line and a starting line or initial line. And there were 2 ways to measure them. The first way to measure them is degrees, and the second way to measure them is radian. And we need to think, why do we use the radian generally? And the reason why we use radian in our trigonometric function generally is because for our degrees, we could express it in terms of number, but it had a special units that looks like a small circle that express those numbers in terms of degrees. And for degrees, we needed a special units. However, for a radian, we're expressing the angle in terms of the real number. And the real number is just number, except we can't use the negative number since there is no negative number, such as 1, 4, 5, 5.7, which is a decimal, 1/2, which is a fraction, pi, and e. And we have to remember that pi, especially pi, is not a letter. It is all set up the number, the decimal 3.14 going on in terms of one term as pi. So pi was included in terms of real number, and using this number to describe a angle, we call it in terms of radians. And we could define the radian in our sector, and the sector was the part of the circle formed with the radius and the arc length of our circle. And again, the radius is half of the diameter in our circle, and the arc length is the circumference of our circle, part of our circle, but we are thinking about it in terms of the sector. So we define the radian, where the radius of our circle, not circle but sector, is equal to 1, and the arc length, the length of the arc length is also equal to 1, where radius and the arc length are exactly equivalent. We defined the data, which is an angle in terms of radian, as 1. And we could figure out that the radian in terms of sector is a measurement of the angle that expressed the ratios. And the ratios was between the radius of our sector and the arc length for our sector. And this was the basic definitions for the radian. And in order to think about more to derive a formula, we thought about the second example, where the radius is usually be assumed as the positive 1 unless something else is stated. And when the arc length increased as 2, because this is a ratio, so the arc length doesn't really have to be 1, then the following theta, which is a angle in terms of radian, increased and became positive 2. And lastly, when we had the sector with the radius of 1 and the arc length is shrink arc length as 1/2, then we define theta as radian. When the radius is 1 and the arc length is 1/2, the following radian angle is 1/2. So using this information, we could derive when we notate the arc length as the value of the L and the radius as the value of the R, then the angle that is formed between the two radius and the arc lengths as a theta. Then we could write a proportion expression where the L is equal to R, which is a radius, times the theta, which is an angle in terms of radian. And this is a expression that shows the ratios or proportions between the arc lengths and the radius. And we express the proportion in terms of the angle radian. And this was the introduction for the radian, and we're going to talk about the basic informations or the relationship between the radians and degrees, and how to convert the radians to degrees or degrees to radians in the next video.